Doofenshmirtz Incorporated!
You know what they say, those who read their handout have an advantage for today's discussion. Today, you are in for a treat. We will be talking about chapters 4, 5, 6, and 10 of Thomas Kuhn's The Structure of Scientific Revolutions.
Oh, hi, Dr. Doofenshmirtz. Good to see you.
Oh, hello there.
What are you up to today?
Oh, nothing. Just talking to these people about Thomas Kuhn's book.
Oh, really? That sounds fun. Can we stay?
If you must.
Perfect. This is going to be the best discussion ever. Are you ready, Ferb?
Yep.
It appears that Ferb is a little more vocal today than usual.
Very well. Sit and listen. Beginning with chapter 4 entitled Normal Science as Puzzle Solving. In this chapter, Thomas Kuhn, one of the most influential philosophers of science of the 20th century, introduces normal science and its relationship with the scientific paradigm. He explains how the concept of normal science shapes scientific progress.
Isn't it true that this chapter highlights how normal science functions as a process by solving problems within a well-defined paradigm, wherein progress is measured by the ability to extend and refine the existing framework rather than seeking to challenge or overturn it? For those who are unaware, a paradigm is a set of perceptions, rules, and methodologies that scientists in a given field agree on. Kuhn argues that the success of normal science lies in its ability to provide a foundation for precise and detailed work.
This chapter puts an emphasis on the fact that normal science is inherently conservative, as it aims to preserve and extend the existing paradigm. Scientists are often resistant to ideas or discoveries that fall outside the accepted framework.
But still, the paradigm-driven puzzle solving is essential to the progress of science as it lays the groundwork for future innovations, even if those innovations come through a later paradigm shift.
We've been talking about normal science since a while ago, yet we haven't really truly defined it. According to Kuhn, normal science is not about testing or questioning fundamental assumptions, but instead, it's about solving problems that the paradigm presents. Other than that, Kuhn notes that normal science operates under strict rules and traditions dictated by the current paradigm. These rules dictate what the scientific problem is and the tools to be used, and the acceptable methods of solving puzzles. Normal science ultimately leads to the recognition of anomalies and crises, which we will encounter later in the discussion.
Now onto the puzzle solving part. Kuhn notes that normal science is about puzzle solving. These puzzles are defined by the paradigm and have solutions that scientists expect to find. Now think of it like this. When you do puzzles, there's a picture on the box and all the puzzle pieces fit together in a specific way. The goal of these puzzles are to find where the pieces fit and complete the image. Now, to relate it to normal science, the paradigm serves as a picture on the box since the paradigm provides the framework and a set of rules that guide scientists in their research. Then, scientists solve the puzzle or the problem by working within the paradigm to fit the data, observations, and theories together in a coherent way. Now, what's interesting is that the goal isn't to discover something totally new or revolutionary during normal science. It's more about refining and extending what's already known. The paradigm provides the tools and the direction for how scientists approach their work. It sets the limits for what counts as a solvable problem. Kuhn also believes that scientists are motivated less by a desire to be useful and more by a desire to prove how great they are and for people to admire their intelligence. This metaphor conveys how scientists' work within an established framework is more step-by-step, constrained by the paradigm, and how this framework both enables and limits scientific progress until the anomalies become too great to ignore.
I like the way Kuhn described it as puzzle solving because it makes it clear that the scientists are not necessarily thinking about the bigger picture or challenging the paradigm. They're working within it, trying to figure out smaller, more detailed problems. It's almost like they're testing the paradigm's boundaries but not necessarily questioning the framework itself.
Kuhn doesn't think that a paradigm is defined merely by its important rules, and instead, They can shape normal scientific work even in the absence of specific laws or methods. And the paradigm itself provides a lot of implicit guidance. It's not just about following strict rules. Kuhn mentions that the methods, standards, and even the questions scientists consider legitimate are all shaped by the paradigm. But it's interesting that scientists rarely focus on anomalies that don't fit the paradigm, or at least not at first.
During normal science, scientists are really focused on the puzzles that the paradigm says can be solved. They're not thinking about throwing away the whole puzzle, and that's what Kuhn means when he says normal science is conservative. Scientists are actually trying to preserve the paradigm by solving these puzzles, not challenge it. Only when the paradigm can't handle the anomalies does the idea of a paradigm shift come into play. But that's more of a revolutionary process, not exactly what we see in normal science.
Speaking of paradigms, in Chapter 5 entitled The Priority of Paradigms, Kuhn discusses why these are important in normal science, and he provides reasons why normal science could be determined without the discovery of rules, but instead with paradigms.
Kuhn describes paradigms as something that is shown in recurrent and quasi-standard illustrations. Basically, paradigms show how theories and concepts are applied in practice.
Kuhn stated that normal science can be determined by the direct inspection of paradigms. Kuhn explained this direct inspection by comparing it with Ludwig Wittgenstein's philosophical idea, family.
The overlapping and crisscross resemblance of paradigms provides scientists an idea on conducting normal science. Instead of referring to fixed and comprehensive rules, normal science operates through shared practices, examples, and methods.
The commonality of scientific concepts is that they resemble existing paradigms that scientists are exposed to, rather than the adhering to a full set of rules. Kuhn further discussed the significance of paradigms by stating reasons why normal science can operate through paradigms without the intervention of rules.
His first reason, severe difficulty in discovering rules that guided a particular normal scientific tradition, similarly illustrates how a philosopher finds it difficult to list what all the games have in common. Thus, isolating a paradigm is easier than listing all the rules in a scientific tradition for a scientist to explore and solve problems. Kuhn then explains that the nature of scientific education is applying theories, laws, and concepts. Scientists also learn these paradigms through historical development. For instance, if a student of Newtonian dynamics learns the meaning of terms like force, mass, space, and time, he learns less with these definitions if he will not be observing and participating in the application of these concepts to real problems. At some point, the student of scientific education will intuitively create his own abstractions or concepts, but these will be accepted through successful research by his application on established paradigms, which can be understood without the recourse of rules.
This leads us to Kuhn's third reason. Normal science can proceed without rules as long as the relevant scientific community accepts a particular problem solution achieved. This means that scientists intuitively follow paradigms because it provides a framework of models and expectations. Hence, they do not try to rationalize them. But if a paradigm seems to be insecure or if a crisis occurs, scientists question the laws and methods of a certain paradigm, which makes the rules important in this scenario. Lastly, paradigms make the diversity of scientific fields easier to understand. Because science is not one unified study, paradigms guide specific fields while rules, such as the scientific method, are more universal and applied across disciplines. Given that the paradigms are related by resemblance, they can overlap with different fields, but if a major shift occurs in one field, it doesn't automatically lead to changes in other fields.
Kuhn argues that paradigms are more than just the formal rules or theories. They're about shared practices and assumptions. For instance, he mentions how scientists learn through examples or what he calls exemplars. These are specific instances of problem solving that scientists can model their work on. Well, those exemplars are interesting because they show how paradigms are passed down without necessarily being codified into rules. Scientists learn how to apply these examples to new problems, which means they're often relying on intuition or a sense of what fits the paradigm, not just on explicit instructions. It's fascinating how this explains why scientists can work so efficiently even when they're not consciously aware of every rule they're following. They know, for example, what counts as a legitimate problem, what kind of results are expected, and what methods are appropriate, all because of the paradigm.
Furthermore, on philosophical paradigms, the alternative view holds that scientific revolutions have not changed the way scientists see the world, but rather how they interpret their observations. For example, your instructor asks you to get a lengthwise paper, but you only have one whole sheet of paper, so your blockmate decided to just tear it into half. But it turned out not pretty good, so your other blockmate brought scissors to cut it into half. But instead of solving the problem got even worse because the paper is no longer divided lengthwise. Kuhn then introduced small and large revolutions. He explained that small revolutions affect only the members of a subspecialty, while large revolutions lead to profound changes in how scientists understand the world. An example of this is if each member of physical scientists were taught the laws of quantum physics. Most of them will use these laws at some point in their research. They, however, do not learn the same applications of these laws because their communities are large and diverse. Therefore, not every physical scientist is affected by the changes in quantum mechanics.
In summary, Chapter 5 makes clear that paradigms aren't rigid set of rules, but flexible frameworks that shape how science is practiced. They create stability, but they also set the stage for crisis when anomalies appear.
Now, let's take a look into Chapter 6 entitled Anomaly and the Emergence of Scientific Discoveries. Beginning with the concept of anomalies, Kuhn defines anomalies as results or observations that don't fit within the expected outcomes predicted by the reigning paradigm. These anomalies are not immediately seen as a threat to the paradigm. Scientists often first try to explain them away or assume that the anomalies are results from an experimental error. But when they persist, anomalies challenge the existing framework of normal science. It's like when the certain data or phenomena can't be explained by the current laws and theories. At first, scientists might ignore them, but eventually they realize that something bigger is at play. Anomalies can be the seeds of scientific revolutions. I think Kuhn's key insight is that science doesn't advance by steady accumulation, but by these moments when anomalies force a rethinking of the fundamentals.
Now, let's talk about the emergence of scientific discoveries. Anomalies play a major role in triggering discoveries. It's not just that scientists see something unexpected and immediately understand its importance. Kuhn argues that recognizing anomalies is a gradual process. Often, scientists will spend a lot of time trying to force the anomaly to fit into the existing paradigm before realizing it represents something fundamentally new. Kuhn describes this as a two-stage process. First, there's the awareness that something doesn't quite fit, and second, there's the realization that the anomaly couldn't be resolved within the current paradigm, which calls for a new way of thinking. This is when the possibility of a new discovery emerges.
Now let's talk about paradigm shifts. When anomalies pile up and the existing paradigm can't handle them, scientists may be forced to adopt a new paradigm that can explain the anomalies. These shifts are revolutionary because they change how scientists see the world. Kuhn emphasizes that these shifts are not just about new theories taking old theories' place. Instead, they completely reframe the way problems are defined and how scientific work is conducted. A paradigm shift alters the very questions scientists ask. For example, after Copernicus proposed the heliocentric model, astronomy wasn't just about adjusting planetary orbits. the entire method and understanding of celestial mechanics change.
Now, these anomalies become important because of their ability to change the status quo. They are the cracks in the structures of normal science that eventually led to breakthroughs. Kuhn shows us that without anomalies, science might never evolve. Here is an example from his chapter. The shift from phlogiston theory to Lavoisier's oxygen theory, it marked a major paradigm shift in chemistry. Lavoisier's discovery that combustion involved combining with oxygen resolves anomalies that the old theory couldn't explain. This led to the rejection of phlogiston's theory. Kuhn really helped us appreciate that science is not just a straightforward march towards truth. It's a dynamic process shaped by these periods of disruption and transformation. Anomalies are a fundamental part of that process because they open the door to new ways of thinking.
In conclusion, anomalies are crucial for the emergence of scientific discoveries. They challenge the existing paradigm, and when they accumulate, they can lead to paradigm shifts that redefine science itself. It's not always a smooth or immediate process, but anomalies are what drive revolutions in science. Kuhn shows us that without anomalies, science would be stuck in a cycle of just filling in details of established paradigms rather than making truly groundbreaking advances.
Lastly, we have Chapter 10, Revolutions as Changes of Worldview. In this chapter, Kuhn delves into the nature and influence of scientific revolutions on scientists. This chapter begins by emphasizing that when a paradigm shift occurs, scientists perceive or see their research engagement differently. Kuhn says scientific revolutions aren't just about adding new theories or improving theories, but completely overturning the way scientists see the world. Like, it's a complete break from the past, not just a step forward.
The previous chapter explains the role of anomalies in paradigm shifts. When these unexplained observations accumulate and cannot be explained by a current paradigm, crises occur. These scenarios can lead to paradigm shifts, thus introducing the concept of incommensurability, which refers to the idea that scientific paradigms cannot be directly compared to old paradigms because they operate under different rules and perceptions. The idea of incommensurability is fascinating. He's saying that when a paradigm comes in, it doesn't just explain the anomalies from the old one. It redefines the entire field, including what counts as a fact, what problems are considered worth solving, and even how those problems are approached.
When a scientific revolution takes place, the perception of scientists must be re-educated because they operate with a new paradigm. The Copernican revolution demonstrates how scientists re-educated themselves with the presence of a new paradigm. Scientists abandoned their previous assumption, the Earth being the center of the universe, and learned to understand and accept the new paradigm, the heliocentric model, which suggests that the Earth and other planets orbit around the Sun. When a scientific revolution takes place, the perception of scientists must be re-educated because they operate with a new paradigm. The Copernican revolution demonstrates how scientists re-educated themselves with the presence of a new paradigm. Scientists abandoned their previous assumption, the Earth being the center of the universe, and learned to understand and accept the new paradigm, the heliocentric model, which suggests that the Earth and other planets orbit around the Sun.
Lastly, let's talk about the concept of Gestalt shift. Kuhn likens the shift from one paradigm to another to a Gestalt shift, representing the deep transformation in perception and understanding, similar to the visual shift where the same image can be seen in a completely different way.
Now, take the example of the duck and the rabbit. Take a look at this image. What do you see? Okay, I'm just going to assume that you see a duck. Now, this is the beak, these are the wings, these are their webbed feet. You get the picture. Let's rotate the image vertically. Now, what do you see? I see a rabbit. Now, here are the ears, the fluffy cotton tail, and here are their legs. So, can you see the concept of Gestalt shift come into picture? Different images can present different meanings if they're looked at from different perspectives.
And that's all for today, everybody. I hope you are enlightened about Kuhn and chapters 4, 5, 6, and 10 of his book. See you all next summer. Bye!